Section 9.3, Geometric Sequences and Series. So last section, looking at arithmetic, specifically the common difference. Oh, let's go look at it, okay. Common difference, kind of like the slope of a linear function. How you get from one term to the next, you're adding a certain amount. That amount could be positive or negative. This section we're looking at geometric sequences. So specifically, there's a common ratio between terms. Ratio meaning division. So a sub 2 divided by a sub 1, or a sub 3 divided by a sub 2, a sub 4 divided by a sub 3, so on. If you get the same answer every time, you have r, which is a common ratio. Just be aware that r cannot equal 0. That would be a very boring sequence, okay? Now r could be 1, that's slightly less boring. That's different, but kind of the same. It can happen, but it's still very boring, okay? And then the nth term of a geometric sequence. So whereas with arithmetic, there was that n minus 1 times d that gave you the common difference you're adding, how many times you added it. Now we have n minus 1 as an exponent on r. So how many times do you multiply r to your first term? So finding the 12th term of the geometric sequence that starts with 5, 15, and 45. So we want n to be the 12th term. We have a sub 1, what we're starting with, which is our first term in the sequence we're given, that's 5. And then r. Take our third term divided by a second. So a term divided by the one before it. And you get 3. Kind of check yourself. The second term divided by the first. You get 3 also. So our nth term of an arithmetic sequence, a sub 1 times r to the power n minus 1. So now let's plug in everything we know. A sub n, our first term, let's zoom out a little, is 5. Our common ratio is 3 to the power 12 minus 1, more commonly known as 11. So then you get hold of this wonderful thing called a calculator. Do parentheses 5, parentheses 3 to the power of 12 minus 1, 11. So pretty simple calculations. Oh, that got big. But multiplying 3 11 times to 5, 885,735. Geometric sequences can get very big very quickly, kind of like exponential functions. Now some, again, of a finite geometric sequence. The formula is a little more complicated than arithmetic. You have your first term, a sub 1, and then times a fraction. In the numerator, 1 minus r to the n, your ratio, and then n, how many terms you're adding up. the number of terms, n for the number, over just 1 minus r one time. So it's pretty important to identify those three things, a sub 1, r, and n. So to look at this first example, n, our first term, and our ratio. Well, n, number of terms adding up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 terms. Our ratio is the number we're raising to a power, so 0.3. And for your first term, it's important that you plug in your lower bound. So 4 times 0.3 to the power 1 minus 1. So 0, 0.3 to the 0 is 1, 4 times 1 is 4. So we have n, we have a sub 1, we have r. So we're going to put all those together. Our summation of the first 12 is a sub 1, which is 4, 1 minus our rate, 0.3, to the 12th power over 1 minus 0.3. And you plug all that into a calculator, you get about 5.714. Now let's look at example B. Okay? It looks pretty similar to example A, but there's one little difference in that exponent. So we want to find the three things we need, n, a sub 1, and r. R again, the number you're raising to a power, 0.3. N from 1 to 12, so 12 terms. A sub 1. Go ahead, plug in your first term, plug in your lower bound. So 4 times 0.3 to the first power, gonna get 1.2 instead of the previous 4. So put all that together. The sum of the first 12 terms, our first term, 1.2, times 1 minus 0.3 to the 12, over 1 minus 0.3, and you plug it into your calculator. Be careful with parentheses and the numerator and denominator. Remember, the calculator is very dumb. Plug in exactly what you wanted to calculate. It will not imply anything about the context of the problem. Make sure you tell it exactly what to do. And with the first term being changed, we see the summation has changed. Also, let me move that around. There. See a difference of about 4. Hey, our first term in the previous example was 4. Now this new sum, because we have the ratio one more time, we have it I times, not I minus 1 times. That initial 4 was left out. So it's important that you identify those three things every time for every problem. They won't always be the same. from problem to problem based upon how the geometric sequence is defined. Now we can have infinite geometric summations if the absolute value of r is less than 1. So any kind of fraction from 0 to 1, positive or negative. Because think, what happens if your ratio is like 0.5? Gets raised to the second, raised to the third, raised to the fourth, raised to the fifth, and so on. That fraction gets infinitely small. Not to say it never happens, but it gets infinitesimally small. It becomes insignificant. So this r to the infinity power cancels out. It's essentially 1 minus 0. A sub 1 goes up to the top. So your formula is A sub 1 over 1 minus r. So you don't need to worry about n because we're adding up infinitely many terms. You really can't do that practically. So we only need a sub 1 and we only need r. So find those for each problem. Check your work with my complete notes online.